Welcome to Module 2, Session 2 of Engineering Statistics and Linear Algebra course. The contents of Session 2 are bivariate expectations, correlation and covariance of random variables x and y. We'll understand what is uncorrelated and orthogonal of random variables x and y. We'll see independent x and y, correlation coefficient of x and y, problem examples, and lastly, we'll look at the assignment questions. First, we'll understand what is bivariate expectations. By this time, you know what is expectation of a single random variable as you have studied in module 1. Now we'll study expectations for bivariate random variable, right? We know for single random variable, the expectation is given as what? E of x is equal to integration minus infinity to infinity x fx of x dx. Now for bivariate random variables x and y, where g x comma y is a function of random variables x and y, the expectation is given as e g x comma y, which is equal to integration minus infinity to infinity, integration minus infinity to infinity g x comma y f x y x comma y dx dy here. Right? Now, if this function g x comma y happens to be a function of only one random variable, right? Here the random variable is x. Now this is a function of only random variable x. Now this expectation will reduce to, right, or modify to e gx is equal to integration minus infinity to infinity gx integration minus infinity to infinity fxy x comma y dy dx. Now this is equal to integration minus infinity to infinity g of x. As I said here, since it is a function of only random variable x, so that this will be fx of x into dx here. Now we'll see correlation of random variable x and y. What is the correlation of x and y? The correlation of random variable x and y is the expected value of the product of x and y, and it is given by EXY, the expected correlation of x and y. EXY is equal to integration minus infinity to infinity, integration minus infinity to infinity, xy, fxy, x comma y, dx, dy. Here, when I say expectation, it is conceptually same as what? Averaging. Now, if you see this product, what we have, 1 by n summation I is equal to 1 to n xi yi. Here, depending on this product value, right? What is the value what we have it here? If I call this product value here, if this product is greater than 0, if it is greater, if the product is greater than 0, we call it as what? Positive correlation. If the product is less than 0, we say it is negative correlation. If the product tends to 0, we say the random variables are uncorrelated. Here, as I said here, if the product is greater than 0, this is a product, we call it as a positive correlation. If this product is less than 0, we call it as a negative correlation. And if the product sums to 0 or near to 0, we call it as the random variables x and y are uncorrelated. Now we'll see covariance of random variables x and y. If the random variables do not have means of 0, if the means of x and y are not 0, then the covariance is defined as covariance of xy is equal to expectation x minus of mu x, y minus of mu y. What is mu x? Mu x is expectation of x, mu y, the mean of x and mean of y. Now evaluate this one, evaluate. This will be what? X, y, mu x, y, x, mu y, mu x, mu y. Okay, minus minus will be plus, and this will be minus and minus. So that how do you now apply the expectation operator for this one? E xy minus mu of x. This is E of y minus mu y E of x plus mu x, mu y. Now this is expectation of xy minus mu x, mu y. Ey is nothing but the mean of y. You write it as mu y minus mu y. E of x is nothing but mu of x plus mu x, mu y. Now just by looking at this one, what we have? Mu x, mu y, mu x, mu y. So that these two get cancelled. So that what we have? The covariance of xy is equal to expectation of xy minus mean of x multiplied by mean of y. This is the definition for covariance of random variable x and y. Now, when we say that the random variables x and y are uncorrelated, if the covariance of random variable x and y is equal to 0, we say that the random variables x and y are uncorrelated. For uncorrelated random variables x and y, now how the above equation reduced? Since the covariance is 0, what was the previous example we have? Covariance is xy here, right? Since this is 0 here, if I take this mu x, mu y on the other side of the equal to sign here, what we get now? E xy is equal to mu x, mu y. So that what we have? E xy is equal to mu x, mu y for uncorrelated random variables x and y. Now, when you say that the random variables x and y are orthogonal, if the expectation of x and y is 0, right, it means that the random variables x and y are orthogonal, right? Where E xy is equal to 0, we call it as orthogonal. For orthogonal, what we have from the covariance equation, as I said here, the expectation of x and y is 0. Since this is 0, covariance of xy is equal to what? Is equal to, this is 0 in here, so that it will be minus mu x, mu y. So that this will be reduced to, for orthogonal, covariance of xy is equal to minus mu x, mu y. The mean of x multiplied with the mean of y. Now, independent x and y now, right? Now we already defined the correlation for x and y. What is the correlation we defined here? E xy is equal to integration minus infinity to infinity, minus infinity to infinity, xy, fxy, x comma y dx dy. Now for this nth moment, in fact, we studied for single random variable, the second order, third order, right? E of xn is a thing, what integration minus infinity infinity x of n fx of x dx. Similarly, for bivariate random variable x and y, now how you define the nth joint moment for the random variables x and y. Now here the expectation is given as what? E xn ym integration minus infinity to infinity, integration minus infinity to infinity. Here xn, x raised to n, y raised to the power m, fx of x, fy of y, dx dy. Here we've written as fx of x and fy of y because for independent random variables x and y, we write it as fx of x multiplied by fy of y. Now this integration you can write it as minus infinity to infinity x of n, fx of x dx, it is a function of x, integration minus infinity infinity y of m, fy of y dy, as it is a function of y. Now what is this one now? What is this one and this one? We know from the formula for expectation for single random variable for nth order, mth order, how do you write it? E of x of n, E of y of n here, right? Here, independence means uncorrelated. the random variables are uncorrelated, but the reverse is not true. Now, we'll look at what is correlation coefficient of random variables x and y. A correlation coefficient denoted by rho xy is defined by rho xy is equal to covariance of xy divided by sigma x multiplied by sigma y. Consider the one deterministic equation x between the random variables x and y. Now we will take the equation as y is equal to ax plus b. Now how do you write? Now for this equation, apply the expectation operator. How do you write it? E of y is equal to what? You can write it as mu of y. This is equal to a is a constant. Apply the expectation operator E of x plus b. Now E of x is nothing but mu of x, a mu x plus b. Covariance of xy is equal to what now? E. Now covariance relation, we know it. How do you write it? E x minus of mu x, ax plus b minus of a mu x minus b. How did we write this one? What is y here? Y is ax plus b. So that in the place of y, we have written it as ax plus b. And for minus mu y, we have written it as what? What is mu y here? A mu x plus b. Since we have minus sign, minus a of mu x minus of b. Now, how do you write this one? E x minus of mu x, a x minus of mu x. Now, what is the covariance of xy now? It is equal to a and sigma square of x here. Right? Everyone understand this one? How do we write this one now? Now we'll look at the problem examples. Find marginal densities, means of x and y, correlation between x and y, covariance between x and y for the given bivariate probability density function. Now, what is the given probability density function here? It is given here. Now, for this one, you need to find the marginal densities, the means of x and y, mu x and mu y, ex, ey, you need to calculate, and the correlation between x and y. And lastly, we need to calculate the covariance. Now, what is the given PDF in this example? Exy is x comma y is equal to 1 by 4 delta x delta y plus 1 by 4 delta x minus of 1 delta y plus 1 by 4 delta x delta y minus of 1 plus 1 by 4 delta x minus of 1 delta y minus of 1. The marginal density for random variable x is given by, we know the marginal density formula. Now here I'm considering the random variable x. For random variable x, what is the formula we have it? Fx of x is equal to integration minus infinity to infinity fxy, x comma of y, dy. Now substitute for the joint PDF which is given in the problem. Substitute in this integration minus infinity infinity dy. Now here, since it is a function of y, 1 by 4 dx integration minus infinity infinity d delta y dy plus again 1 by 4 delta x minus of 1 integration minus infinity infinity delta y dy plus 1 by 4 delta x integration minus infinity to infinity delta y minus of 1 dy plus next what we have it 1 by 4 delta x minus of 1 integration minus infinity delta y minus of 1 dy. Now evaluate this integration. Once you evaluate the integration with respect to dy, what you get now 1 by 4 delta x plus 1 by 4 delta x minus of 1 plus 1 by 4 delta x plus 1 by 4 delta x minus of 1. So that this integration will become 1. So that you get it as this 4 terms. Now again what we have 1 by 4 delta x here. Again we have 1 by 4 delta x. 1 by 4 plus 1 by 4 will be 1 by 2. So that you get 1 by 2 delta x plus 1 by 2. Again, you can see here 1 by 4 plus 1 by 4 delta x minus of 1. So that it will reduce to 1 by 2 delta x minus of 1. Right? This is the marginal density for random variable x. Similarly, calculate the marginal density for the random variable y. What is the formula for this one? fy of y is equal to integration minus infinity to infinity fxy x comma of y dx. Now you can write this integration as minus infinity to infinity 1 by 4 delta x dy plus 1 by 4 delta x minus 1 delta y plus 1 by 4 delta x delta y minus 1 plus 1 by 4 delta x minus 1 delta y minus 1 dx. Now it's a function of dx. So that you take the y terms outside. 1 by 4 delta y integration minus 1 to minus infinity delta y dx plus 1 by 4 delta y integration minus infinity to infinity delta x minus 1 dx plus 1 by 4 delta y minus 1 integration minus infinity to infinity delta x dx plus 1 by 4 delta y minus 1 integration minus infinity delta x minus 1 dx. Now again, for this, since it is a function of x and the integration will become 1, you can write it as 1 by 4 delta y plus 1 by 4 delta y plus 1 by 4 delta y minus 1, 1 by 4 delta y minus 1. We have 1 by 4 delta y minus 1. We have again 2, 1 by 4 delta y. So that it will reduce to 1 by 2 delta y plus 1 by 2 delta y minus 1. This is the marginal density for the random variable y. Next, what we need to calculate the mean of random variable x and y. Now, what is the formula for random variable? We know the formula from single random variable, the expectation of x and y. Mu x is equal to ex is equal to integration minus infinity to infinity x fx of x dx. Now substitute for this one now. Now what is fx of x? What we got it here? 1 by 2 delta x plus 1 by 2 delta x minus of 1. Now substitute for fx of x here. So that how do you write it? X delta x dx integration minus infinity to infinity plus 1 by 2 integration minus infinity x delta x minus of 1 dx. Now evaluate this integration. What you get? X square by 2. Here also x square by 2. Now this will be 1 by 2 in multiplied by 1 by 2 plus 1 by 2. Again, this will be 1 by 2. So that what is the equation for this one? This will be 1 by 4 plus 1 by 4 will be how much? 1 by 2. So that the mean of random variable x is 1 by 2. Now similarly, do calculate the expectation of the mean of random variable y. The procedure is same as what we calculated for random variable x. Now what is fy of y here? 1 by 2 delta y plus 1 by 2 delta y minus 1. Substitute here and evaluate the integration. Substitute the values, you get it as 1 by 2, 1 by 2. Evaluate this one, you get it as, and simplify 1 by 2, you get it. Next, find the correlation between random variables x and y. What is the definition we have? Integration minus infinity to infinity, minus infinity to infinity, xy, fxy, x comma y, dx, dy. Now substitute the values here. 1 by 4 x dx dy dx dy. Now substitute for fxy x comma of y. Now what we xy is common. The first term what we have is delta x delta y. The second term what we have delta x minus 1 delta y, delta x delta y minus 1 and delta x minus 1 delta y minus 1. Right? Now evaluate this one. Now integrate with respect to x, you get x square by 2. Similarly for this one, integrate x square by 2, x square by 2 and x square by 2 here, right? And substitute the values, you get 1 by 2, 1 by 2. Since it is x square by 1, you get it as 1 by 2, 1 by 2, 1 by 2 here. Now evaluate the integration with respect to dy here. Y dy we have it, y dy. Now what you get for this integration? Now for this one, y dy, y dy minus of 1 here. Now you can see just by looking at this, 1 by 2 plus 1 by 2 will be 1. So that integration minus infinity to infinity y dy dy plus similarly what we have 1 by 2 plus 1 by 2 will be 1. Integration minus infinity infinity y dy minus of 1 dy. This is equal to 1 by 4. Now evaluate this integration, you get it as y square by 2 plus y square by 2. And this will be 1 by 2 plus 1 by 2. And so that you get it as what? 1 by 4 here. So that what is the correlation of random variables x and y? It is equal to 1 by 4 here. Now we know that expectation of xy is equal to expectation of x, expectation of y here for independent random variables, right? Now, what is the expectation of xy? We got it as how much now? We got it as 1 by 4 here. Now, what is the expectation of x here? Expectation of x, we got it as 1 by 2. Expectation of y, we got it as 1 by 2. So that when we multiply ex multiplied by ey, you get it as what? 1 by 4. So that what we know here, expectation of xy is equal to expectation of x multiplied by expectation of y. So that we can say that the random variables x and y are independent. And since the random variables are independent, we can say that the covariance is equal to 0. Covariance is equal to 0 here. Now we'll go to the second problem. The mean and variance of random variables are -2 and 3. The mean and variance of random variable y are 3 and 5. The covariance of xy is equal to -0.8. What are the correlation coefficient rho of xy and correlation exy? Now, what are the data given in the given problem statement? The mean and variance are given for both random variable x and y, and also the covariance of x and y is given as -0.8. Now, what you need to calculate? The correlation coefficient rho of x, y. Now, what is the formula for this one? Covariance of xy divided by sigma x multiplied by sigma y. Now, what is -0.8? Now, what is sigma x here? Now, here, what is given here? The variance is given, right? So that now what is sigma? Now it is sigma here, right? Now variance is under sigma square x. So that what is sigma x then? Square root of 3. Sigma y is, for y it is given as the variance is 5. So that sigma y will be square root of 5. Evaluate this one, simplify, you get it as -0.206. So that what is the correlation coefficient? It is equal to -0.206. Next, what you need to calculate? The correlation. Now we know from the covariance formula, covariance xy is equal to exy minus mu x mu y. Now, what are the values which is given here? We need to calculate E of xy. Covariance, we know it, and we know the mean of x and y. Now, exy will be what? -0.8 plus substitute for mu x and mu y, -2, -3. And simplify this one, you get it as -6.8. This is the correlation exy is equal to -6.8. We'll go to the third problem. The mean and variance of random variables are -2 and 3. The mean and variance of y are 3 and 5. The correlation coefficient rho xy is 0.7. What are the covariance x and y and correlation exy? Now, if you compare this problem with the previous example here, it is similar as the mean and variance for random variable x and y is given. Now, in this problem, the correlation coefficient is given instead of covariance as it was given in example 2 here. Now, what is the correlation coefficient here? It is 0.7. Now, what we need to calculate? Covariance, and also we need to calculate the correlation, right? Now, use the formulas, substitute the values for all the mean and the correlation coefficient. You get the covariance as what? 2.711. Similarly, how do you calculate the correlation? Similar to the previous example, substitute for, since we calculate the covariance value here, substitute for covariance value, and mean of x and mean of y is given in this problem statement. Substitute here, simplify the expression, you get it as -3.2889. Now, these are the 3 assignment questions. Thank you.